Okay, it's 5:30, so let's go ahead and get started. All right, good evening, everybody. How's everybody feeling today?
Good. How are you, Professor?
Good, good. Yeah, it's end of week 10, so yeah, definitely at the time of the semester is, yeah, as good as it goes. Yeah, it's I'm tired. I know you guys are pretty exhausted too at this point, and we're all tired together, but we're still in this, for a few more weeks, so we got to finish strong. Okay. So the plan for today is we're going to go over a new set of lecture notes. So today we're going to start our foray into multi-dimensional finite elements. So this is probably going to be a whole new thing for a lot of people, except for a couple holdovers from 410 from last year. I know there's a couple of you guys in the class. So this will be a little bit of a review, but we're going to take this, a lot farther than what we did back in 410. Mostly because this is going to be the subject of your guys' projects. So the next few weeks are going to be really crucial for information for that. So we're going to be building a lot of what we did for the 1D stuff, but we're going to be applying it to 2D. So we're not going to go into 3D because 3D is kind of way too much stuff, just to way too much calculations to do by hand. But I think 2D is kind of a good place where you encounter a lot of problems that you don't see in 1D, and going from 2D to 3D is not as big a jump as going from 1D to 2D. Okay. So are there any questions I can answer about what we covered, what we've been covering before, or on the homework, or anything that I can answer before we get started? Okay, so let's go ahead and get rolling. Okay. Question. So the question is that the homework if the homework is due this Friday. So let me double check on that. Yes, the homework is due this Friday at 11:59 p.m. That's correct. Okay. So the our first order of business is going to be kind of introducing the mathematics and just introducing the concepts of 2D and 3D FEM. Okay. And so I'm going to call this multi-dimensional FEM, but the only D's above one is just 2D and 3D. All right, so the question is, is there any way we can change the homework due date to this Sunday? I'm okay with that. Yeah, I'm okay with changing the due date of the homework to this Sunday. If it'll help you guys out. Yeah, especially because I know a lot of you guys have evacuated due to the fires. So I'm perfectly fine with extending the due date to this Sunday because I don't have the next homework planned yet. So and I'm probably not going to start grading until next week. So. Okay, so let's have the homework due. Homework 3 is going to be due this Sunday at 11:59 instead. Okay. Great. Yeah, no problem. Okay. So this is going to be just we're going to start on just the mathematical. I call this the mathematical preliminaries for 2D and 3D FEM. I'll just say it's just the intro to 2D, 3D FEM, okay? Okay. And so, for the past couple of weeks, we've been working on one-dimensional problems, right? And so we did 1D elasticity, and then we did 1D heat conduction, right? And so we did not only just the strong form and the weak form, and also the finite element form, but on Monday we saw how that stuff is implemented in MATLAB. Okay. And so these problems, they're cute. I mean, then they're kind of a good place to start, but they're not really that practical for solving, kind of real life problems. Because, first of all, if you have a one-dimensional problem, usually it's very easy just to solve the problem exactly, in the strong form, just like we saw. But even just thinking just practically, there's just not many things in the world that are strictly just one dimension. Okay. And so if you want to do some practical problems, which is where finite elements really benefits, you need to use multi-D. Okay. All right. And so the most practical thing would be to cover 3D finite elements. And that's 3D finite elements is obviously what's the back end for commercial software like ANSYS. Okay. But in terms of theory, 3D FEM really gets kind of messy, and I think a lot of times the message kind of gets lost in the details. For this class, you know, we're going to be focusing mostly on 2D, but just know that, you know, a lot of the concepts and things that we'll cover in 2D can extend into 3D. It's just that 3D is just a lot more work. Okay. Okay. And so, you know, there's going to be two kind of big changes here. So the first thing is that we saw in one dimensions that our equations that we looked at were ordinary differential equations. And the reason for that was because we only had one spatial variable that we needed to worry about. And so in 2D and 3D, you know, we have both, we have now not only X, but also Y. And in 3D, we have the Z direction too, okay? And so what this means is that our governing equations, are now not going to be ordinary differential equations, but partial differential equations. Okay? Okay. So now it's going to be a lot harder to find exact solutions. So I know that there's methods out there to solve PDEs, but practically speaking, you know, those kind of analytical techniques for PDEs, they aren't used that often in practice. You know, a lot of times you're going to solve PDEs with some kind of computer software, just because it's just way easier to do. Okay, that's not to say that analytical methods don't have a place. So I don't want you guys going to Dr. Weiss and saying that, you know, Dr. Tran says that analytical methods for PDEs are useless. You know, all those have their place, right? And mostly, you know, they help you build the intuition for solving those problems. But you know, for a lot of practical things, you know, solving like your heat conduction or solving your elasticity, those are done with some computer program just because it's a lot easier. Okay. Another thing that's going to be big for multidimensional problems is that you know, we're going to use a lot of vector algebra and vector calculus. Okay. And so because we're working in multiple dimensions, you know, a lot of these concepts are going to be important. And we're going to review some of the most important things from these guys, you know, as we move forward. Okay. Yeah, don't say that. She probably would kill me at the very least, or at least probably like rip my face off. Dr. Weiss can be kind of scary sometimes. Okay, any questions on this before we go over some basic definitions? Okay. All right, so let's go over some basic definitions, okay? Okay. And so even though we're in multiple dimensions, you know, our definition for a boundary value problem stays the same, okay? Okay. And so remember, there's two components to a boundary value problem. So the first component is going to be our governing equation. Okay. Okay. And then the other component is going to be boundary conditions. Okay. It's just that how we interpret these are going to be different. Okay. And so we've already seen on the previous page that our governing equations are going to be partial differential equations now. But also in multiple dimensions, our concept of a boundary is going to be different. Okay. And so first, let's go over, you know, how our domains are going to change. Okay. Okay. So remember, the domain is the kind of the area or the geometry on which we're going to be solving our equations. Okay. And so we've done one-dimensional problems. And so in 1D, our domain was simply just a line, right? Okay. And so if we go one step up from this, in 2D, our domain is, instead of a line, is going to be a surface. And in 3D, our domain is going to be a volume, okay? Which, in retrospect is, something obvious, but it's, I want to go, state it explicitly, okay? Okay. And another thing that's going to change is our solution variables, okay? Right? And so in 1D, our solution variable was just a function of just one variable, right? And so it could be X, it could be Y, but there was only just one unknown, right? So as you saw in homework 3, we're solving for just T of X or T of Y or U of X or U of Y, right? So there's just one independent variable. And so in 2 dimensions, we're going to have dependence on both of the spatial coordinates, okay? And so for instance, we might have T of X and Y, okay? Okay. And in 3 dimensions, of course, we're going to have dependency on all 3 spatial dimensions, so X, Y, and Z, okay? And we're not going to go over it in this class, but another dimension that can be used for finite elements is time, okay? And so, implicitly what we've been covering in this class is just all steady problems, so things that don't change in time, but there's also, you can also have some effects that change with time as well, okay? So we're not going to go through that in this class. That's usually a subject for like a follow-up finite element class, which we currently don't have here at Fullerton, but just know that time can also be a variable here as well. Okay. And one other note that I'm going to make is that we're not going to be going into it too much because we're mostly going to stick to heat transfer. But if your solution variable was a vector, say if you're solving for elasticity in a structural problem, or if you're solving for velocity in like Navier-Stokes, your solution also becomes a vector itself, okay? And so like if you're solving like a 2D elasticity problem, you're not only going to solve for just, displacement, but you have to solve for displacement in the X direction and then displacement in the Y direction too, okay? And in 3D, you would solve for displacement in the X, Y, and Z direction. Right? But again, we're mostly just going to stick to heat transfer, so our solution variable is going to be a scalar. Okay? Yeah, definitely. Yeah. So if you have any kind of phase change, that's always a time dependent process. So that's definitely going to have a time dependence on there. Okay. Any questions on this? Okay. Okay. And so next thing I want to talk about is just the concept of a boundary, because this is going to be important because this is where we apply our boundary conditions. Okay. And so remember, what the boundary basically is it defines kind of the exterior or the edges of our domain. Okay. Okay. And so in 1D, right? In 1D, our boundary conditions were applied at points. Okay. Right. And so because our domain was a line, right? So the exteriors of the line are just going to be the endpoints. And so when we applied our boundary conditions, they were just on the 2 points right there. Okay. Right. And so now let's extend this up to 2D. Okay. And so for a 2D surface, it might look something like this. Okay. And so for a 2D surface, what defines kind of the exterior of the surface? It's going to be lines, right? And so the boundaries for a 2D surface, or in other words, where we apply our boundary conditions, okay, they're going to be applied on edges or lines. Okay? Right? And so that's actually going to make a pretty big difference on how we, we apply our boundary conditions. Okay. And then in 3D, I'll just kind of mention this. The exterior of a 3-dimensional volume is going to be its surface. Okay. And so for 3-dimensional finite elements, our boundary conditions are applied on surfaces. And so one easy way that you can think of it is that the boundaries for any kind of domain is always one dimension less than your domain itself, okay? So for 1D, you know, we have a one-dimensional line. You go one dimension less than that, 0D doesn't, you know, technically exist, but, you know, it's, you can consider that is a point, okay? And so for 2D, you know, our domain is a surface. You go one dimension lower than that is a line or an edge, okay? That's where you apply your boundary condition. And then for 3D, you know, our domain is a volume, and so one dimension less than that is a surface, and that's where you apply the boundary conditions. Okay. Okay. Any questions on this so far? Okay. And so one other concept that's going to be important is this idea of an outward unit normal. Okay. And so we've kind of already seen this, you know, in the we saw it briefly in the finite element forms. But when I talk about the outward unit normal, all I mean is just some vector that points kind of perpendicular to the surface, pointing to the outside. Okay. Right. And so just by convention, you know, whenever you talk about like a normal vector, that's always going to point outwards from your surface. Okay. So I mean, there's, of course, there's such thing as an inward facing normal, but it's just not used much in practice because outward is kind of just the standard. Okay. If you ask me why, you know, maybe someone just flipped a coin back then and just that seems to make the most sense because it does seem a little bit arbitrary. Okay. But just know that, you know, when you talk about normal vectors, we talk about it facing outwards. Okay. And so now let's talk about partial derivatives. Okay. I think everyone hopefully should be familiar with the concept of a partial derivative. And, you know, these are needed because, you know, since our functions, you know, they depend on multiple variables. Okay. We can take derivatives in each of the variables independently. Okay. And so let's say that we have a function that's a function of x, y, and z. Okay. And so we can take the partial derivative with respect to x. Okay. So we said partial f, partial x. Okay. And so you know, mathematically, this looks like this. Okay? And so this is going to be the limit as delta x approaches 0. Okay? Of f of x plus delta x yz minus f of x y z all divided by delta x. Okay. And so that's what it means to have a partial derivative. So you basically just vary one of the dimensions and you find the change in that direction. Okay. And so by a similar token, you can also have partial f, partial y, and partial f, partial z. Okay. So you can take partial derivatives in any direction. Okay. Okay. And if we can take derivatives, we can also take a double derivative. So we can have partial squared f, partial x squared. Okay. We can also have mixed derivatives actually too. Okay. Right. And so mixed derivatives is nothing more than just you take a derivative in one direction, then you take that and you take the derivative in the next direction after that. Okay. And so in practice, you know, you usually don't see these a lot, at least in kind of the domains of mechanical engineering, like structural mechanics, fluid mechanics, heat transfer. You know, a mixed derivative is very, very rare unless it's, you know, some kind of very specialized model. But, you know, they do exist out there, and they're used for other stuff, but just not really for mechanical engineering. So, you know, I just wanted to acknowledge that they exist, but then, you know, we're not actually going to use it all for too much. Okay, any questions on that? Okay. Okay, and so the next thing I want to review is just some of the various vector calculus operators. Okay. Okay. And so, you know, we're going to need these operators because basically what we're going to do is we're going to extend our strong and weak forms in one dimensions to multiple dimensions. And, you know, just so that we don't have to write tons of derivatives all day, usually we have this kind of shorthand notation for these guys to help us, you know, save some space in writing. Okay. And so there's three that I want to go over. The last one kind of being a combination of the first two. Okay. And so the first one is a gradient operator. And so the gradient operator, you know, this is an operator in vector calculus. It's probably one of the first ones that you learn. And this, you can kind of almost think of this as like an expanded derivative. Okay. And so what the gradient is going to do is that it's going to take your function and then take the derivative of that function in every single direction, and then save that, you know, in separate components. Okay. And so let's say that we have a function f. Okay. Okay. And the function f is a function of x, y, and z. Okay. And so if we take the gradient of this, and so the gradient is given by this symbol right here. Okay. And so the gradient symbol is this kind of upside down triangle, right? And so the name for this symbol, if you're curious, I actually didn't learn this until, you know, somewhat recently. And so the name of this symbol is called a nabla. Okay. And so if you're either using LaTeX or using the equation editor in Microsoft Word, okay, this is how you call it. And so the gradient of this would be actually a vector, okay? And the vector would be the derivative of f in each of the different directions. Okay? And so here this assumes that f is a scalar function. Okay? Okay? And so this kind of highlights, you know, one really important characteristic of the gradient is that a gradient increases the dimensionality of a function. Okay. Okay. And so if you take the gradient of a scalar, you're going to get a vector. And if you take the gradient of a vector, you actually get a matrix, okay? And so let's say that we have some vector quantity u, okay? So u can be a velocity or can be a displacement, okay? And so I'm not going to write out the entire thing, but you can imagine, you know, if u has components ux, uy, and uz, you know, you would have a matrix that looks like this. Okay. And so in that case, you know, you're going to take the derivative of each of the three components of u in each of the three different directions, x, y, and z. Okay. And so you don't need to write this down. So this is just, you know, just for your information. Okay. Okay. And then there's going to be one more column here, which, you know, is going to be there as well. Okay. And so if you took 520 with me last year, you know, this is our velocity gradient. Okay. And so the gradient, remember, it's the reason I kind of put this definition first up here as an expanded derivative is that you can kind of almost think of it as you take whatever function you have, which is a scalar or a vector, and you just take the derivative of it in each of the different directions and kind of store that as a thing. Okay. Okay. Any questions on the gradient? Okay. All right. So that's the first operator that I want to go over. And so the next operator I want to go over is the divergence. Okay. And so the divergence can almost be thought of as kind of like the opposite of a gradient. Okay. And so the gradient, we're going to take our nabla operator and then we're going to dot product it with a vector. Okay. Okay. And so let's say that we have something like this. Okay. And so the divergence is given by something that looks like this. We take nabla and we take the dot product with the vector. Okay. And then mathematically it's going to look like this. Okay. Okay. And so you're going to take the components, you're going to take the partial derivatives of each component in that specific direction. So we're going to take partial ux, partial x, partial uy, partial y, partial uz, partial z, okay? And then you're going to add them all up together, okay? And so the reason I call this the kind of the opposite of a gradient is that it's going to decrease the dimensionality by one. And so if you take the divergence of a vector, you turn it into a scalar, okay? Okay. And so kind of the easiest one is going from vector to scalar, but you can also take the divergence of a matrix too, and it'll turn it into a vector. But that one's a little bit more complicated, and we're not going to deal with that because we're just going to stick to 2D stuff. But I just want to let you know that that's there. Okay. And so the last operator that I want to go over is called the Laplacian. Okay. And so the Laplacian is kind of the combination of both of these guys. Okay. And so the way that we get the Laplacian is we take the divergence of a gradient. Okay. And so let's take our scalar function f, okay, that we started with before. And so let's take the gradient of it. Okay. And so if f is a scalar function, if we take the gradient of that scalar function, then we get a vector. Okay. Then we can take that vector, and then we can take the divergence of it, and we can turn it back into a scalar. Okay. So it kind of seems like we're going in circles, but actually, you know, each time we transform, we apply another derivative, okay? And so what this results in is actually a term with second order derivatives, okay? And so the shorthand notation for Laplacian is given by nabla squared, okay? And then mathematically, it has this value right here. So we take partial squared f, partial x squared, plus partial squared f, partial y squared, plus partial squared f, partial z squared, okay? And so this is the Laplacian, okay? Right. And so this is going to be important because if you remember, you know, the equations that we worked in 1D were one-dimensional equations, and they had, you know, they had second order derivatives. So, you know, this Laplacian here is basically how we're going to get the second order derivatives in our equations. Okay. Okay. Any questions on this? Okay. Okay. So that's kind of the very brief review of vector calculus. So I just wanted to hopefully just remind you what all these different operators mean. Okay. And now we're gonna learn one pretty important theorem and formula called Green's theorem and Green's formula. Okay. And you know, the reason we're going to be going through this is that it's going to serve a very specific purpose for us. Okay. And that purpose is that it's going to allow us to perform integration by parts in 2D and 3D. Okay? And so if you remember, you know, from our one-dimensional case, when we went from the strong form to the weak form, you know, a very key component of that was being able to do integration by parts. And remember, we did that to balance the derivative. Okay. And so we're going to need to do the same thing in multiple dimensions, except, you know, they don't teach multidimensional integration by parts in your basic calculus class. So, you know, the way that we're going to do is we're going to rely on this theorem by Green. Okay. Okay. And so just to kind of remind you what you know, what the one-dimensional integration by parts is, I'm just going to write it down again right here. Okay. And so in 1D we had you know, integral from 0 to L, okay, of w of x, which is our weighting function, times d dx of EA times du dx, and so this is for elasticity, okay, dx. And so that on the left right there, that was our strong form of the equations, which had, you know, the second derivative on the u term. And so by applying integration by parts, we can balance this derivatives onto that w term, okay? And so by applying integration by parts, we get two guys. And so our first guy was this one right here. So we have w of x times EA du dx, okay? And this was evaluated at our Neumann boundary, okay? And then from this, we're going to subtract an additional term, which has our balanced derivatives, okay? And so our additional term is going to be integral of dw dx times EA du dx, okay? dx, okay? And so this right here was our integration by parts in one dimension, okay? And I bring this up because I want to kind of, you know, classify these terms right here, okay? And so this first term, you know, we can kind of almost think of this as like the boundary term, okay? Because it's a term that's evaluated on the boundary of our domain, okay? And then this term on the right here, this is our interior term with the balanced derivative. Okay. And so what Green's theorem and Green's formula is going to do is that it's going to give us it's going to give us the same results. We're going to get a term that's going to be evaluated on the boundary, and a term that's going to be evaluated on the interior with the balanced derivative. It's just that they're going to look different, because you're going to utilize the vector calculus operations that we went over just previously. But the core concept of those terms are still going to be the same. Okay. Any questions on this? Okay. All right. So for the sake of time, I'm going to skip through the derivation of Green's theorem and Green's formula. Because in the grand scheme of things in this class, it's not as important. Okay. Oh, so the question is, so the work's the same with Fourier's conduction equation? Yes, that's correct. Yeah. So I'm going to be presenting you Green's theorem and Green's function, or Green's formula here, in terms of just a generic function. So you can apply it for both Fourier's law for conduction and also for elasticity as well. Yeah. Okay. So again, I'm going to skip through the derivation, but it's in the notes if you're interested. But it's the result that we really are interested in, and normally derivations are used if there's something within the proof there that's going to be more interesting in the grand scheme of things in the class. But in this case, it's literally just a math proof, which math is cool, math is great, but we're trying to do finite elements here, not just math. So if you're interested in the proof, it's there for your notes, but I'm just going to skip to the result because that's going to be the thing that's going to be most important. Okay, so first I'm going to present to you Green's theorem in 3D. Okay. Or I should say Green's formula. I keep getting the two mixed up. Okay, so in 3D, Green's formula looks like this. So we're going to have a triple integral, okay, of W. Okay, so W has the same interpretation as before, so that's going to be our weighting function. Okay. Then to that, we're going to multiply the Laplacian of T. Okay, and so T right there, that's going to be our solution variable. Okay. And so on the left right here, you can see the same conundrum that we had before, where this term has an unbalanced derivative. Okay. And so what this is going to be equal to is there are going to be two integrals on the right. Okay. And so the first one is going to be a surface integral. Okay. Okay. And so this right here is a surface integral. Okay. And this is going to be integrated on the boundary of our of the volume. Okay. Okay. And so I'm using the same color scheme as on the previous page, just to let you know that this is the same as our boundary term. Actually, no, I didn't use the same color scheme. So this should be blue right here. But this term, it represents a boundary term, right? And then from this, we're going to subtract a triple integral. Okay. And this triple integral is going to be gradient of W dot product with gradient of T, okay, d dv. Okay. And then this term right here, you can see, because now instead of having the Laplacian on T, now we have the gradient on W and a gradient on T. And so this right here is our balanced derivative term. Okay. And so you can see, we've replaced, a lot of the symbols here, our derivatives with, our vector calculus symbols, but the idea behind Green's formula is still the same. And so, the idea behind this is that, we're taking an integral here with an unbalanced derivative, and then we're splitting it up into one, a boundary term that we're going to evaluate on the boundary, and that's going to become our Neumann boundary condition. And two, our second term is, something that has a balanced derivative. Okay? And remember, the reason we do this is because in this situation right here, okay, our t only has one derivative. Okay? And what this means is that, we're going to have weaker continuity requirements on t. And so when we go in and we assume a form of the solution, that gives us a lot more freedom to choose something like a linear function, which is going to be a lot more easy to evaluate. Okay, so this is a 3D version. So, we're not going to be working with this one, directly. But, the 2D version is, very, very similar to this. And I'm going to write it on the next page. Okay? But does that kind of make sense about how we kind of generalize the kind of the one-dimensional form for integration by parts into 3 dimensions? And so don't worry about evaluating these just yet, because that's going to be the subject of the next few weeks. But I just want to just kind of introduce the idea that, just because we're in multiple dimensions doesn't mean we can't do integration by parts. It's just that we have to do it a little bit differently because we're in multiple dimensions, and the way we do that is with Green's form. Okay, and so let me give you the 2-dimensional version of Green's formula. Okay, so it's going to look very similar to the 3-dimensional version, except the number of integrals is going to go down. Okay. All right, so first we have the left-hand side, and so on the left-hand side we have W, Laplacian of t, dA. Okay, and so since we're in 2D, our integral becomes an area integral. Okay. Okay. And so next we have our boundary integral. Okay. And remember, for a 2-dimensional case, our boundary is defined as a line. Okay. Okay. And so this integral that we're applying right here, which kind of looks like a music note, I use that notation to denote a line integral. Okay. And again, we'll go over how to evaluate this in a later lecture, but I just want to kind of get that concept down that this boundary term is going to be one dimension less than our domain. Okay. Yeah. So the integration variable here is ds. Yeah. So s is typically the variable that you use to denote a line integral. Yeah. And so it's an integral on a line instead of on a surface. Okay. And then from this, we're going to subtract out a double integral on our domain, but with balanced derivatives. Okay. And so we have a double integral of gradient of w dot with gradient of t. Okay. And this is on area. Okay. And so this, just like before, this has balanced derivatives. Okay. And so schematically, it's probably going to look something like this. So here we have our 2D domain. Okay. And so I'm going to give the symbol omega to denote the domain. Okay. And then when we evaluate the line integral, the line integral is going to be evaluated on this path around here. Okay. And so our line integral is going to be evaluated just on this path, but only for the Neumann boundary conditions. Okay. And so that's just to kind of help you visualize, what's going on with this integral. Okay. Any questions on this before we move on to heat conduction? And so if you're following along with the lecture notes, I kind of breezed through, lecture notes 10, which is kind of the mathematical preliminary. So I didn't want to spend too much time on it just because it is just math, and hopefully a lot of it is review. But I do want to get into more of the heat conduction stuff. So I haven't posted these lecture notes yet, but I will kind of right after the class right now, okay? And so what we're going to go over next is 2D heat conduction with finite elements. Okay. And so in two-dimensional problems, just because it's, if you're dealing with kind of vector quantities like elasticity, it's kind of a pain because you have to solve everything twice. I'm going to focus most of our 2D discussion on heat conduction, okay? And the nice thing about heat conduction is that our solution variable is just simply temperature. Whoa. Okay. And the nice thing about temperature is that it's a scalar. Okay. Okay. And so scalars are great because there's only one of them, so there's no 2 or 3 components. Okay. And so I'm going to be calling this heat conduction all throughout, but actually, this equation that we're going to be solving can actually be applied to any kind of scalar diffusion equation, okay? And so actually, if you've taken like a heat transfer and a mass transfer course, mass transfer, like the diffusion of, like, say you drop like food coloring into a glass of water, the transport of that food coloring actually follows the exact same equation as heat transfer. So traditionally, we call it heat transfer, but it's actually used for a lot of other applications. Okay. And so the difference now is that we're in 2D. So we're going to develop the theory in kind of the same way. And so we're going to start with the strong form equations. Then we're going to derive the weak form. And then from the weak form, then we're going to derive the finite element form. Okay. And so along the way, you're going to be seeing, a lot of the same ideas that we saw in 1D finite elements, but we're going to generalize that to multiple dimensions. Okay. Okay. And so first, let's get some kind of vocabulary out of the way. Okay. Okay. And so let's talk about how we kind of characterize our domain. Okay. And so since we're in 2D, we can have any kind of arbitrary 2D domain. So it doesn't have to be a blob. I just draw a blob just because it's just to illustrate that it's arbitrary. Okay. And so again, just like on the previous page, we're going to use the symbol omega to denote the interior of the domain. Okay. Right. And so the interior of the domain is going to be significant because this is where we're going to solve the heat equation, or this is where we're going to solve our differential equation. Okay. 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 And so on our domain, we're going to have a thermal generation term. Okay. Okay. So S of X and Y. This is going to be thermal generation. Okay. And so this has the same kind of physical meaning and physical intuition as the 1D case. It's just the only difference now is that it's a function of 2 variables instead of 1. So instead of just having S of X or S of Y, now we have S of X and Y. Okay, and so now let's talk boundaries. Okay. And so I'm going to split the boundary into kind of 2 different sections here. Okay. Okay. And so in purple right here, I'm going to call this our Dirichlet boundary. And so the symbol I'm going to give this is going to be gamma u. Okay. And on the Dirichlet boundary, this is where we supply our Dirichlet boundary conditions. Okay. And so remember, for 2D cases, we're no longer just supplying boundary conditions at a single point. We're supplying them over an entire edge. Okay. And then everything else, or all the rest of the boundary, okay, which I'll kind of trace out in green right here. Okay. This is going to be our Neumann boundary. Okay. And I'm going to give this a symbol gamma t. Okay. And so gamma t, this is the locations where we're going to specify our Neumann boundary conditions. Okay. Okay. And of course, you know, our solution here is going to be t of x and y. Okay. Okay. And that's what we're going to be solving for. That's going to be our temperature solution. Okay. Okay. And so I draw this figure here not to tell you that, you know, that the Dirichlet boundary and the Neumann boundary have to look like this exactly. But I just want to tell you that, you know, when we're solving these problems, we always make a distinction. You know, what parts of our boundary are going to be where we apply the Dirichlet boundary condition, and what parts of the boundary are we going to apply our Neumann boundary condition. Okay. And so they don't have to be next to each other. They don't have to be, you know, contiguous like this. But I just want you to you know, just keep in mind that we're going to be applying these, you know, boundary conditions on different parts of the boundaries, you know, and we have to have a way to kind of label them one way or another. Okay. Okay. And then one last thing I always forget. We have our outward normal vector n. Okay. Okay. Any questions on just the definition of the domain and the boundaries? Okay. Okay, and so now that we have the boundary, you know, defined, you know, just the kind of the highlights of that are we have omega for the interior of the domain, we have gamma gamma u for the Dirichlet boundary conditions, and we have gamma t for the Neumann boundary conditions. Okay? And so the next step here would be to specify our governing equations. Okay? And so let's start with the strong form. Okay. So I'm not going to derive this equation because you know, you probably already did it in a previous heat transfer class. Okay? But the equation looks like this. Okay? So we have K, and so K right here, that's our thermal conductivity. And then to that, we're going to multiply partial squared T, partial X squared, plus partial squared T, partial Y squared. Okay. Right. And to this, we're going to add our thermal generation term. Okay, so that's S of X and Y. And all this is going to be equal to 0. Okay. So just to kind of remind you, this K right here is thermal conductivity. Okay. As S of X, Y right here, this is thermal generation. Okay. And so there's a shorthand form for this, just to kind of you know, help you avoid writing these derivatives so often. And it utilizes an operator that we just went over. Okay. And that's the Laplacian. Okay. Okay. And so the Laplacian operator is what you'll traditionally see, you know, in a lot of textbooks on multidimensional stuff, just because it's a lot easier to write. Okay. But remember, the Laplacian operator represents this fact right here. Okay. And so if you have the Laplacian of t in 2D, that's nothing more than just partial squared t partial x squared plus partial squared t partial y squared. Okay. Okay. And so this is our strong form of the equations. And so if you wanted to solve this exactly, you're going to need some very sophisticated methods for you know, solving PDEs. Okay. And so we're not going to go over that in this class, because that's the subject of, you know, another class. But instead, you know, we're going to solve this equation through the finite element method. Okay. Okay. And so let's discuss boundary conditions, okay, and at least how they're formulated. Okay. And so our boundary conditions are given by the following. So let's say, let's start with, you know, a Dirichlet boundary condition. Okay. And so the way we specify a Dirichlet boundary condition is just the same. Okay. And so if we take t and we evaluate it at our Dirichlet boundary, right? So our Dirichlet boundary is given by gamma u. Okay. And so that's going to make it so that we specify t as some specified temperature T naught. Okay. And so the definition of this is still the same, and the way we actually apply it to the global system is going to be the same as well. Okay. And so we're going to, just like we saw in 1D, we're going to zero out the row, we're going to put 1 on the diagonal, and then we're going to put the Dirichlet value on the right hand side. Okay, so let's talk Neumann boundary conditions, just because this ones are a little bit more interesting because they utilize the outward unit normal. Okay. And so for, if we have Q right here, Q bar, this is going to be some kind of heat flux. Okay. And the SI unit for heat flux is going to be watts per meter squared. Okay. The way that we mathematically formulate this for heat conduction is that we do minus K times gradient of T dot product with the normal vector. Okay. Okay. And so this is Fourier's law of heat transfer. Okay. And so what this basically is saying, you know, by taking this dot product in between these two terms right here, by taking that dot product, what we're saying is that the heat flux or any kind of Neumann condition is only going to be the component of the heat flux that comes out of our domain. Okay. Okay. Or in other words, this is going to be denoting any heat flux that crosses our boundary. And so that dot product with the normal vector basically establishes that. And so by taking the dot product, we're implicitly taking the component of delta of the gradient of T that's going to be going out of our domain. Okay. Because remember, when we take the gradient of T, we get a vector out of that. And then by taking the dot product of that with the normal vector, then we get the component going out of our domain. Okay. Okay. Any questions on this? Okay. Okay, and so just as an example, just to kind of show you, you know, how to evaluate this term, let's take a domain where we have kind of just a vertical face, just like this. And let's say that we have a heat flux Q bar that's coming out like this. Okay. And so let's take n hat and let's evaluate its components. Okay. And so since our face here is perfectly vertical, our normal vector is just going to be a unit vector in the x direction. Okay. Okay. And so let's apply our Neumann boundary condition here. Okay. And so our Neumann boundary condition is given by the following. So you have minus k times gradient of t dot product with n. Okay. And so if we write out the components for this, this would be minus k. And then, so gradient of t is going to be dt dx, and then comma, dt dy. Okay. And then we're going to take the dot product with 1 comma 0. Okay. And so if we take this dot product, we have dt dx multiplied by 1. And then to that, we're going to add dt dx multiplied by 0. Okay. And then all we get is minus k partial t partial x. Okay. And then to apply our Neumann boundary condition, this has to be equal to q, q bar. Okay. And so since our heat flux here is only in the x direction, we only use the x component of the temperature gradient when evaluating the Neumann boundary condition. Okay. Right. And so that dot product there is really important because that what that tells us is that we're only going to take the component that goes out of our domain. Okay. And so in this case, the y direction is going to be parallel to our boundary, and in that case, we don't really care about it because it's not crossing our boundary itself. Okay. Okay. Any questions on this? Okay. All right, so that's the strong form of 2D heat conduction. And so now let's go over the weak form. Okay. And so just like in the 1D case, we can derive the weak form. And the way that we're going to do that is we're going to multiply by a weighting function and then integrate over the domain. Okay. And then the other thing that we usually do in the weak form is that we perform integration by parts to balance the derivatives. Okay. 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 And so that was the procedure in 1D. So we're going to follow the exact same procedure in 2D. It's just that the symbols and everything change for 2D, and to perform integration by parts, we have to use Green's formula. Okay. And so one quick note, before we jump into it, is that because we're in 2D, our weighting function also has to be a two-dimensional function. Okay. And since we're in 2D, the integral that we perform here is going to be a double integral. And as we mentioned, the integration by parts is done by Green's formula. Okay, so let's write our strong form of the equations, but I'm gonna rewrite it into a form that's a little bit easier to apply Green's theorem to. Okay, and so our strong form, okay, is given by the following, and so we have k, and so normally here we have the Laplacian, But remember, the Laplacian is nothing more than just the combination of a divergence and a gradient. Okay, it's going to have k times nabla dot product with nabla t, okay, plus s of x comma y equal to 0. Okay. And so first thing, let's multiply this by our weighting function. Okay. And so if we multiply by a weighting function, we have w of x and y, okay, multiplied by k nabla t, okay, plus s of x comma y. Okay. All this is equal to 0. Right? And then let's perform the second part of this is let's integrate. And so to go from this this top equation right here to this bottom one, all I did was just multiply by w of x and y and then integrate it over a domain. Okay? And so our integral in this case is a double integral. And so before moving on with the integration by parts, I'm going to separate these two guys into two different terms. Okay? And so because we have this plus right here, we can separate this into an integral over the Laplacian and then also an integral over the thermal generation term. Okay. Any questions on this before we move on? Okay. Okay, so let's write out those two integrals that result from this. Okay. And so first thing, we're going to have an integral over the Laplacian term. So this is going to be a term with an unbalanced derivative. Okay. And so we have w of x and y multiplied by k multiplied by the divergence of the gradient of t, okay, dA, plus the double integral of w of x and y times s of x and y, okay, dA, okay, and this is equal to 0, okay. And so this term on the right here, we're just gonna leave this alone. Okay. Mostly because there's no derivatives here, and so there's nothing that we need to balance. Okay. And then this term on the left right here, we're going to apply Green's formula to integrate by parts. Okay. And so I wrote about Green's formula in green, but it was total coincidence. Okay, and so let's go ahead and break up this integral. Okay, so I'm going to kind of ignore this first term up here, or this second term, but we'll bring them back in a bit. But the first thing, let's apply Green's formula to this part of this integral. Okay, and so let me write it out again. So we have double integral of w x w of x and y, okay, times k times the divergence of the gradient of t dA, okay? And then by Green's formula, we're going to break this up into two integrals. So the first integral here is going to be a line integral over the boundary. Okay? And so that's going to be an integral with a circle. Okay? W k times gradient of t dot product with n, okay, ds. Remember, this is a line integral over the boundary. Okay. And then from this, we're going to subtract a double integral with a balanced derivative. Okay. So we have double integral of the gradient of w dot product with k times the gradient of t dA. Okay. Okay. And so now that we have these two terms, what we can do is we can plug that back into this expression up here. Okay. And so we're going to replace that first integral with the double derivative on t with this guy right here, so that we have just at most just a single derivative on t. Okay. Okay. Any questions on that so far? Okay. Okay. And so if we do that and we make that substitution, we have the following. Okay. And so first, let's write out our line integral. So we have line integral of w k gradient of t dot product with n ds, okay, minus double integral of gradient of w dot product with k gradient of t dA. Okay. And then to this, we're going to add our source term. This should be a minus right here. Okay. Double integral of w of x and y, s of x and y, dA. Okay. And so at this point, let's look at this term right here. Okay. And so this k times gradient of t dot n. Okay. And so let's replace this by minus q hat. Okay. So this is our Neumann condition, right? Because that's how we define our Neumann condition before. Okay. And so if we take this term, oh, all this is equal to 0, by the way. Okay. And if we take this term and then we move it to the other side of the equation, we can arrive at the weak form for our 2D heat conduction. Okay. Okay. And so if we do that, we are left with the following. So we have double integral of gradient of w dot product with k gradient of t dA. Okay. And so this is the balanced derivative term that I moved to the other side of the equation. Okay. It's going to be equal to minus and line integral over the boundary of w come on iPad, w times q hat ds, okay, plus integral of our source term, or integral of our thermal generation term, sorry, double integral of w of x and y, s of x and y, dA. Okay. And so this right here is the weak form for 2D heat conduction. Okay. Okay. Any questions on this? Okay. And so I'll make one more quick note before we take off for today. And it's, one note that I forgot to mention is that, remember, just because we're in 2D doesn't mean our weighting function doesn't have to follow the same rules, okay? And so remember, in one dimension, one of our rules for a weighting function was that it has to disappear on our Dirichlet boundaries. Okay. And so the same rule is going to apply here too. It's just that it's going to be a little bit more complicated because our Dirichlet boundary is going to be a line instead of just a point. Okay. But it still has to follow that rule. And so, in multiple dimensions, the weighting function still has to disappear on the Dirichlet boundary. Okay. So that's all we got time for this week. Oh, there's a question. So the Q term, yes. So on the Dirichlet boundary, the Q term is not going to be present as well. So this fine integral, you're only going to evaluate this on the Neumann boundary. Okay. Yeah. Okay. So that's all we got time for today. So on next week, what we're going to do is we're going to, see how this is applied for finite elements. Okay. And the interesting thing that we'll see is that in finite elements for 2D, we're going to have a little bit more freedom than in 1D because we can actually choose the shape. Okay. Because in 1D, you only have one choice for a shape, and that's just a line. But in 2D, there's a lot of two-dimensional shapes out there. So we're going to do a triangle and a quadrilateral. So those are the two most common ones. And we'll see how this affects, our element stiffness matrix and element force effect. Okay. But we'll pick this up here on Monday. So thank you everybody for tuning in. Hope everyone stays safe and has a good weekend. And I'll see you guys on Monday. Yep. Thanks everybody. So mysterious phone number, do you have any more questions?